The final transformation we'll look at is a stretch in the x direction, or parallel to the x-axis. It's also called a scaling in the x direction, or parallel to the x-axis, or a stretch along the x-axis. This is probably the most complicated and the most confusing type of transformation that we have to deal with. It's written as f of x maps onto f of ax. As we'll see when we look at the slides in a little while, the value of a is the reciprocal of what's called the scale factor. So if the scale factor was equal to a half, then a would equal 2. And in order to apply the stretch in the x direction, we have to multiply the x values by the scale factor. So if we had a 2 inside of these brackets here, we'd have to multiply the x values by a half. We're using as an example the function x plus 4 multiplied by x minus 2. Or in other words, x squared plus 2x minus 8, which you can see down here. In the text down here, at the moment, we've set a equal to 1. And you can see the roots occur at -4 and +2, as we would expect. The y-intercept is at -8, and the axis of symmetry is at -1. So let's have a look at what happens when we change the value of a. So you can see the shape of the curve is changing. As a becomes more positive, the curve bends more. It's also important to note that the location of the axis of symmetry is changing, and the roots are changing as well. Here we have f of 2x. The scale factor is a half. As you'll remember from before, the roots occurred in the original function at -4 and +2. But by applying the scale factor of a half, we're halving those x values. So our roots are now at -2 and 1, as you can see. And the axis of symmetry is at x equals -1/2. You can also see that the y value of the vertex doesn't change under this transformation. The minimum value of y is -9, and it stays at that minimum value throughout the range of values of a in the transformation. In this particular example, with positive values of a, the vertex and the axis of symmetry lie to the left of the y-axis. As a becomes more positive, the largest value we can give a in this example is 5. We can see the vertex is now just to the left of the y-axis. As we reduce the value of a, let's take it down closer to 0, we can see that the vertex is moving further away to the left of the y-axis. What's going to happen when a is equal to 0 then? Let's have a look. Well, when a is equal to 0, f of x will just equal -8, because all of the x terms will be 0. In fact, the intercept, y equals -8, is the same throughout the range of values of a. It doesn't change under this particular transformation. So when we have a equals 0, we know that we just get the straight line y is equal to -8. What's going to happen when a is less than 0? Well, you can see now that the vertex is on the right of the y-axis. So what in fact is happening is that when a is negative, we get a reflection in the y-axis compared to the case when a is positive. So For the case where a was equal to positive 2, we had roots at -2 and 1, and the vertex was at x is negative 0.5. If we now take the case of a is equal to -2, we'll find the situation is reversed. We've got the reflection in the y-axis, so the roots are now at -1 and 2, and the vertex is at positive 1/2. Okay, let's have a try at some examples for ourselves then.
The horizontal stretch can be one of the most confusing transformations to deal with. It's stated as f of x maps onto f of ax. The first thing to remember is the scale factor is 1 over a. So the number that you see in here isn't actually the scale factor. The scale factor is 1 over a. So if your scale factor was 1/2, the number you would write inside of the function here would be 2. Likewise, if your scale factor was -2, the number you would write inside the function would be -1/2. When we apply the horizontal stretch, or the horizontal scaling, or the stretch parallel to the x-axis, the stretch in the x direction, as it's variously called, we have to multiply the x values by the scale factor, not by the number that's inside of the function here. If we multiply the x values by that number, we'll get the wrong answer. It's important also to remember that the locations of the roots will change if the modulus of a is not equal to 1. The y values of any vertices and also the intercept on the y-axis will not change. If a has a negative value, it's equivalent to reflecting the function in the y-axis, as is shown in this case here. So there are a number of things that you need to remember when applying the horizontal stretch. Let's have a look at an example. Given the graph of f of x below, sketch the graph of f of 1/2 of x. As we said before, we need to be very careful about this number here. This is not the scale factor, it's the reciprocal of the scale factor. So we should write down that our scale factor is going to equal 2. It's the reciprocal of 1/2. Once we know the scale factor, what we have to do is multiply all of the given x values by this scale factor. So anything where there's a value of x is equal to 0 will not change, such as the intercept on the y-axis. Everything else will change its location though, but the corresponding y values will be the same. So let's have a look at the graph on the left-hand side and see what we need to do. We've got a number of points here, and we'll begin with the first of the 3 roots on the left-hand side here. It's at -5, 0. So under the transformation, it's going to be located here at -10, 0. The intercept on the y-axis will be unchanged. It will still be at 0, 5. The vertex at 2, 6 will move to the new location 4, 6. The second root at 5, 0 will move to 10, 0. The vertex at 7, negative 3 will move to 14, negative 3. And the third root at 9, 0 will move to 18, 0. Now we can draw on the sketch. So you can see that f of a half x has the effect of doubling all of the x values. And it stretches out the graph along the x-axis.